Yeah, so hi, I'm Anna, and I'm presenting my work and the work of my supervisors today for our for my master's thesis, which was deep learning based claim matching with multiple negatives training. Here's the outline of the presentation. I first give an overview of the presentation and then an introduction to the topic, our used methods, give a few details of our experiments, and then end with a conclusion and a little discussion. Yeah, okay, what is the topic of our presentation of our work? Our topic was automated fact-checking pipelines, where there are many steps where you can use deep neural networks, for example, checkworthiness or the actual fact-checking in the fact-checking pipeline. But we focused on the claim matching step. Claim matching refers to matching an incoming claim with an already verified claim, so an already fact-checked claim in a database, so that you or the journalist don't have to fact-check things twice. Our proposal in short is a modification of a challenge-winning two-step approach, a two-stage approach, with two steps and two large language models. Our contribution in short was first to modify a loss function using multiple negatives, then to investigate an alternative loss function, which is the ranked list loss, and then expanding the analysis by including a different metric, which is the mean average recall. Yeah, the goal of the claim matching, or the goal of the challenge that the goal of the challenge was to generate a list of relevant ranked verified claims, so from the database of already fact-checked claims. And of course, in the data set, there are incoming claims and claims from the database, and they belong to one another. And we want to match, to rank the matching claim at the highest. So the claim matching challenge that was issued was the CLEF CheckThat 2022 challenge, and it was won by one contribution with a two-step pipeline. And we replicated the results and expand them. So the first step was a sentence T5 fine-tuning, which generates a selection of relevant fact-checked candidates from a database. And in the second step, we re-rank the generated selection of candidates by fine-tuning GPT-Neo, which is a generative LLM. Okay, the data that was provided with the English portion of the data set, which is based on verified, so fact-check claims from Snopes, from the website Snopes, which is about 14,000 verified claims and 1,400 input claims. These input claims here are tweets. Our statistical benchmark is the BM25 algorithm, which is the best matching algorithm. It outputs a ranked list of verified claims for each input, so for each tweet. It generates a list of all the claims, all the fact-check claims in the database. And we also use the top entries in the training of the proposed system in the first step, which I will explain later. A bit of nomenclature for this presentation. When I talk about a match, from now on I'm going to say a positive claim. And if I'm talking about a non-match, then a negative claim. So a match from incoming claim and matching fact-check. Okay, step one is the candidate selection. It is based on fine-tuning sentence T5, which is a sentence transformer based on self-attention. It is a dual encoder model, which is already trained on similarity tasks, and we want to find semantically similar claims. So the loss that was used by the submission was the multiple negatives ranking loss, which is the MNR loss, which is in equation 1. And as you can see, or as I will explain, for an input, you need a tweet, which is TI, a matching claim, which is CI+, and the best ranking non-matching claim from the BM25 algorithm, which is the CJ minus. And what this loss does is comparing all claims in the batch to the tweet and minimizing the distance to the matching or to the positive and maximizing the distance to the negative claims. We now expanded this loss and we expanded it to more negative claims. So in the first equation, we only used one negative, the most high ranking negative, which is the CJ minus. And in the equation 2, you can see here's a sum of 1 to 5 negative claims. So we did training with 1, 2, 3, 4, and 5 of the highest ranking negatives for each claim. Our goal was to give the model even more context than with one negative. Okay, the second step is the generative re-ranking. Here we fine-tuned, we take the fine-tuned ST5 from the first step and generate lists of the 5 most similar claims. Then we combine the input tweet and the 5 ranked claims to fine-tune GPT-Neo. GPT-Neo is a rebuild of GPT-3 XL. And so we fine-tune it so that the most probable outcome is a combination of tweet and the matching claim. So because it's a generative network. The loss functions we used are the ranked list loss, which is a simple, base loss for ranked lists. And then the NL3U, which is based on the base log list log likelihood. This is called the negative log likelihood unlikelihood loss, so NL3U. Then we used a sum of mutual, so prior and posterior information losses, which you can see in equation 3. And then a mixed objective from the challenge winning proposal, which combines the mutual information and the NL3U. Okay, here are also the equations for the losses for the sake of completeness, but I do not have time to explain every single one. In our experiments, we use we use 2 evaluation metrics, which are the mean average precision, so MAP, and the mean average recall, which is MAR. Mean average recall measures in % the matching claims present in at K lists, so in lists that are K long. So in our case, it's always 5 or just 1. And the mean average precision also takes into consideration the placement of the matching claims. Since we only have 1 matching claim for each tweet, the claim can be placed at first place, second place, third place, and so on. And first place gets the best ranking. This also means that MAR is always the upper bound of MAP. And per definition, as can be seen here, MAP1 and MAR1 are the same, so we only report one of them. And the challenge evaluation metric was MAP5, so we also focus on that in the discussion of the results. For our experiments, we used the BM25 as the BM25 performance as our benchmark. And then we have the 5 fine-tuned ST5 models, which are then each fine-tuned, retrained on GPT-Neo on 4 different losses with the re-ranking. So that leads us to 20 distinct trained systems. Yeah, here are also the equations for MAR and MAP for information, and the difference is computationally very small and is just in the equation 11, the one, the scoring. Okay, the results for the first step for the candidate selection can be seen here, where we trained with 1, 2, 3, 4, 5 negatives, as I already stated. The best performing approach is always highlighted in bold, and as we are focusing on MAP5, this is also highlighted in gray. And as can be seen, the performance peaks for 3 negatives, which is the 0.936. And our theory is, so because this is the best performing approach in the first step, that this will also then lead to the best performing in the second step. And we improved in comparison to just 1 negative. We improved it at around 0.5 percentage points. It then declines again for 4 and 5 negatives, while the MAR stays relatively stable. So that tells us that the sorting, that our the map could be improved by sorting, and this is what we are doing with the re-ranking in the second step. This supports our theory that more negatives provide better context, but also shows that if you provide too many negatives, there's too much weight put on the rejection of negatives and too little support on matching really with positives. In the generative re-ranking, now we can see our 20 different systems that I just mentioned. We have the training with the negatives and then the re-ranking with the 4 losses. Again, the best performing approaches are highlighted in bold, and as can be seen, is that the mixed loss performed the best in every training capacity, and the ranked list logs unfortunately performed the worst. The mixed then, when we look at the map 5, peaks for the 2 negatives and mixed loss combination at around 0.958, and our this doesn't match the hypothesis that the 3 negative train would be the best performing, but it is close. And our hypothesis why the mixed loss performs the best is that it includes different aspects of text similarity. It measures mutual information and contrasts it with info about the negative examples. Okay, now here at a glance are our contributions. First, you can see the BM25 performance for the map measure, which already has a good performance at around 0.85. Then we also present the reference winning submission, which is our reproduction of this submission, where the ST5 achieves 0.93, and then the re-ranking of this achieves almost 0.95. And then under that, it highlights our best approach, and our best approach for the first step improves on the submitted first step, and our overall best model, which is the GPT trained with 2 negatives and the mixed loss, achieves a performance of around 0.958, and improves the submission, the challenge winning result at around 1 percentage point, which means that this is a loss reduction of around 20%. In conclusion, our approach was a 2-step claim matching approach by fine-tuning deep neural networks. We generalized the MNR loss by including even more negatives, and our configurations achieved a system which 1 percentage point error rate reduction in the map 1 and map 5 scores, and also improved in the MAR5 score. And for future work, we would like to incorporate even more data, as this was originally planned to be a German work, but there were only English datasets available at the time. And we could also imagine to use more powerful large language models to retrain and fine-tune on our dataset. Yeah, thanks. And if there are any questions, I will happily answer them.